Greetings to all those who have tuned in to this third episode of a topic that we started 2 sessions ago. The title of the topic being Some Tips on Counting. We have already completed 2 such lessons, and in the first lesson we dealt with 2 important principles, and they are known as the first and the second counting principles. And we studied several examples which were applications of these 2 principles. In the second lesson, we moved on to the problem of arranging a collection of objects, and we wanted to know in how many ways can a collection of objects, maybe the letters of a word, be rearranged. And even more generally, the question was, instead of arranging or rearranging all the objects, suppose you take them, take a certain number of those objects and ask how can those objects be chosen in an ordered way. When that happens, we call it an arrangement or a permutation, where the order is of importance, like the letters of a word. ACE, for example, is not the same as CAE, although they use the same letters. So those were called permutations. We now want to move on to the next section where the order is not necessarily of importance. Okay, so let's look at the very first problem on this. Okay, before we launch into that particular question, we did not have time to finish some interesting problems in the second session. So what we will do now is run through those problems and finish off problems regarding the arrangements. Okay, so the first of these problems, as continued from the last lesson, was the following. There are n points on a page, no 3 of which lie on the same straight line. And the question is, straight lines are drawn through these points, each containing at least 2 of the given points. How many lines are there? All right, so the question says you've got several points and you want to find out how many lines there are that connects these points. No 3 of these lie on the same straight line. So if you have, say like that, if you've got 5 points, the question is, how many lines can you draw? So you can draw one line going through that, another line going through those 2 maybe, and so on. I'm not going to do the whole lot. Okay. So how many such lines can be drawn? All right. Now to draw a line, you need to choose a point, or choose 2 points. Those 2 points will determine a unique line. Right? There's only one line that can be drawn through those 2 points. And conversely, if any particular line in this scheme would go through 2 chosen points, which means that the number of lines is equal to the number of ways in which 2 points can be chosen from the given set of points, and there are n of them. So now that leads to the interesting question: in how many ways can 2 points be chosen from n different points? Okay. And the answer to this is quite straightforward, because we already know the answer to this. We already know the answer to this. And the answer is n into n minus 1 over 2, because this is what we proved earlier on. So the number of such lines, let me just put this on. The number of lines is equal to the number of ways of choosing or selecting two points from n points. So here the objects are points, and we're choosing 2 from that, and we know, and that is equal to n into n minus 1 over 2. And that's the answer. Right. So if you got 10 points, for instance, then the number of lines will be 10 times 9 divided by 2. That's 90 over 2, which we know to be 45. So with 10 points, there are 45 lines that can be drawn. Okay, so let me save this and get on. The next problem is given an array of dots like this. Actually, there are 4 times 4, 16 dots. No. Given an array of dots, 16 dots, and they all seem to be arranged quite nicely, okay, in a grid. How many rectangles can be constructed having 4 of these dots as vertices? Okay, now so that's an interesting problem. You could have several rectangles that can be drawn using 4 of those vertices. Maybe I should say that the sides of the rectangles are horizontal or vertical. Okay, so can we just assume that that is the case? Well, I think I'd better just put that down. Assume sides of such rectangles are horizontal or vertical. I'm not counting tilted rectangles. All right, so what do we have to do? That doesn't look easy, because there could be any number of such rectangles. Let's just choose one. For instance, we can choose, say, one like this. That is an example. Or we can choose another one to say like this. Perhaps I should have used different colors here. Okay, so okay, I'm not winning with that one. Okay, so the question is now, how many such rectangles can you draw? And the answer is, well, we have to choose, to draw a rectangle, you have to choose 2 horizontal points and 2 vertical points. Right? So the question is, in how many ways can this be done? Okay, so you can choose 2 horizontal points and then 2 vertical points. You have to choose those 2 and those 2. And then you have to choose the columns. So you have to choose 2 columns from 4 and 2 rows from 4. So a rectangle is completely determined by its rows, its horizontal lines, rows, or its columns. And you can see easily that the number of ways in which you can choose 2 rows is, all right, so let's just say this, a rectangle is determined by its horizontal and vertical lines. Okay, so that's the important thing about this. And then, so the question is, how many ways can you choose the horizontal lines? In how many ways can you choose the horizontal lines? And the answer is, there are 4 horizontal lines you can choose from, and you have to choose 2 of them. So the answer to that question is 4 times 3 divided by 2, because this is what you said. Right? Horizontal lines can be chosen in 4 times 3 divided by 2 ways. And for each such choice, there are, again, you have to choose 2 columns now, 2 vertical lines, 6 vertical lines. To fix the rectangle. So the number of rectangles is 6 times 6. Okay, so to count here, we have to count how is this rectangle constructed. To construct it, you have to choose the horizontal lines And then having chosen the horizontal lines, then you choose the vertical lines. See? Okay, so that is the solution to that problem. Just go back to the diagram. Yeah, just make this quite clear. Why do we say that? What we're saying here is to draw a rectangle, you have to choose these horizontal lines like this. I have to pick two horizontal lines. Say that one, and maybe that one. So there are 6 ways of doing that. And having done that, I have to pick 2 vertical lines now. You can just choose any 2 vertical lines. The moment you do that, then you got your rectangle. See? You have your rectangle. So that is the point. Okay. All right, so let's now get on to the next problem. Now here you have an interesting problem. In how many different ways can Harry, Hagrid and Undila share 13 apples, each getting at least 1? All right, so they've got 13 apples and they want to share these apples, and the question is, how many ways can they do that? See, so there are many ways. The idea is we need to see how can we write 13. Essentially, how can we write 13 as a sum of 3 numbers? Right, this is Harry, call him Harry, Hagrid and Undila. Right? They can share it like this, or they can share it like this, or they can share it as this. There are many ways. So the question is now, how many ways can this be done? It doesn't look like an easy problem because you can write all the things down, but it might take a long time. And having written the whole lot down, you've got no guarantee that you have exhausted every one of them. You remember, each one gets at least 1 apple, right? So it's not an easy problem to do if you just look at it like this. But there is a very clever way of doing this, and I'm going to show you how it's going to be done. What you do is the following. You take the 13 apples and lay them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? And then to break them up into 3 pieces, all I have to do, now this is the interesting thing, all I have to do is to just draw a vertical line somewhere. Suppose I draw this vertical line here. So and suppose the first part of this goes to Harry. So here Harry will get 2. And the second part goes to Hagrid. But for that, I need to draw another vertical line. You can draw it anywhere. You draw it here. but draw it in between two dots, right? So then now you can see, in this case here, Harry gets 7, and here Andila gets 4. Okay, Andila gets 4. So to get a partition, if you like, a partition of 13, you have to break it up into 3 pieces, and essentially you have to draw 2 vertical lines in the spaces. That's the point. You have to draw 2 vertical lines in the spaces. The 2 vertical lines can be anywhere, and they would divide it up into 3 pieces. Now observe, you can't draw a vertical line here, because it means that somebody gets nothing, and everybody needs to get at least 1. If I put a vertical line here, then Harry will get nothing. That's not allowed. So the first vertical line will have to be here. See? So the question is, in how many ways can you draw 2 vertical lines, right? In the way we have said it. And the answer is, now you have to see how many spaces there are. Right? So the question is, how many spaces are there? So if I just remove just these 2 vertical lines which you've chosen here, and then count the number of spaces, let me do this. Okay, so you count. There's 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the 11, 12. So there are actually 12 spaces in which you can draw 2 vertical lines. So the problem is now the very much more interesting problem, or much easier problem. The question is, in how many ways can you choose 2 spaces from 12 spaces, right? See, the objects here become spaces. In how many ways can you choose 2 spaces? Each time you choose 2 spaces, then you could got 2 vertical lines, and each time you have 2 vertical lines, you have a breakup of 13, right? And conversely, every time you have a breakup of 13, you really are creating 2 spaces. If I say 3 plus 5 plus 5, for instance, the first one has got this particular spacing. 3 plus 5, see. So that one has got that spacing. So the question is, in how many ways can you choose 2 spaces from 12 spaces? So finally the question is, the answer is equal to the number of ways of choosing 2 spaces from 12 spaces. And as we saw, we already know the answer to this. This is 12 times 11 times 2, because here the objects are spaces. The number of ways of choosing 2 objects from n objects is n into n minus 1 over 2, and we are using this again. Alright, so there are 66 ways. Okay. Alright, then now let's get on to the next thing, and I think we've finished what we were supposed to do the last time. So I'm going to just save this. We'll save this and get on to the next one. Okay. So now we go on to a new problem. And this is the problem. Given a set having n elements, the question is, how many subsets does the set have if each subset has exactly r elements? Now you've got a subset of a set, so it will have fewer elements than the set. So here we got r is smaller than n, because n is the number of elements in the whole set. And you could have a subset having no elements, the so-called empty set. So we allow that. So how many subsets does the set have where each subset has r elements? So exactly the same way of, another way of asking exactly the same question is, in how many ways can r objects be selected from n objects? Right? Because we are choosing a subset. A subset means you are making a particular selection having r objects. So this is a selection. The question is, how many ways can you select r objects from n objects? Now we already know the answer to this question when r equals 2. We said if you want to select 2 objects from n objects, we already know the answer. The answer is n into n minus 1 over 2. So in other words, what we are doing here is actually generalizing what we did earlier on. Instead of saying that we want to select 2 objects, we are saying now that we want to select a number which is different from 2, and it could be 3 or 4, whatever it is. So in how many ways can you select, say, 3 objects from n objects, or 10 objects from 50 objects, whatever. So let's take a particular case and analyze how it works here. So if you consider the special case where n equals 5, in other words, you've got a set having 5 elements, and you want to choose an r is equal to 3, so all your subsets will have 3 elements. So your set has got 5 elements, just name them A, B, C, D, E. And as we saw now, these can be points, or these can be spaces, or whatever. So we just call them objects, but we give names to these objects like this. These are not numbers, but they are objects. We can list all the 3 element subsets. We can actually write all the 3 element subsets, and I've done it here. Right? And we see that we have 10 possible subsets. So the number of subsets having 3 elements is 10. That's the crux of the thing. Now, by the way, I'm not writing anything down here, but if you look carefully, you will see that in this case here, for instance, I've left out 2 elements, namely D and E. Here too, I've left out 2 elements, right? C and E. In each case, you are leaving out 2 elements. And every time you have 2 elements, if you choose 2 elements, that means the remaining parts will be your 3 element subset. So the point I'm trying to make here is, it's a subtle point. The point is that the number of 3 element subsets, we call this a 3 element subset, is equal to the number of 2 element subsets. Right? Because each one can be matched with that 2 element subsets which have been left out. So that way the number of 3 element subsets is equal to 2 element subsets. It's a very important fact that if you've got 5 elements, the number of 3 element subsets is equal to the number of 2 element subsets. All right, we'll say this, we will come across this later on, and hopefully I will cover that. So now let's see how these sets are created. Now watch. Note that when we create a subset like ACB, right? Now you notice ACB is not here. The reason for that is I've chosen ABC. And the set ACB is the same as ABC. Right? So this subset is the same as that. It's got the elements A, B, and C in it. Right? So here, the order is not important. Very important point. This is not like the previous problem where the order was important. There was an arrangement, right? The word ABC or ACB is different from the word ABC. So there, you counted that twice, or counted it separately. But here, you don't count this separately. These two are the same subset. All right, so suppose we want to count the number of subsets without looking at this thing here. And you say, okay, suppose there are, we don't know how many subsets there are. But we'll just make a point here that each of these 10 subsets, they create arrangements. If I take this and I twist the question around and I say, how many arrangements are there if you take 3 objects from 5 objects? Now, if I take a particular choice of 3 objects, this thing here can be arranged, where the order is important, that can be arranged in 3 factorial ways, as we saw. And 3 factorial is 6 ways. So this gives you 6 possible arrangements. There are 6 words that you can make with that particular combination. Likewise, each of these will create 6 new words because you've got new letters, right? And it goes all the way up to the 10th one. So if you want to count the number of arrangements altogether, then it is really 10 times 3 factorial. Because each of these 10 can be arranged in 3 factorial. But remember, we know the number of arrangements of 3 objects taken from 5. This is equal to the number of arrangements of 3 objects taken from 5. And the last one, we saw that this is really, it's a box argument. You've got 5 objects. The first one can be chosen in 5 ways. The second one can be chosen in 4 ways. And the third one in 3 ways. So that answer is 60. 5 times 4 times 3. That's an arrangement. Right? The order is important. So we have this interesting thing here, and this thing here was actually, we saw that this is the same as 5 factorial over 5 minus 3 factorial. That was the last thing we did. Oh, I'm sorry, 5 minus 2. 5 minus 2 factorial. Right? Five minus 3. Sorry, 5 minus 3. Okay, we had, in that situation, we had the number of arrangements of R objects taken from N objects is, let me, so what we had there was, this is 10 times 3 factorial is 60. So eventually, if we rewrite this thing down, that it's so the answer to our question is therefore, this is the key step here. 10 times 3 factorial is 60. So how do you get the 10? The 10 is actually can be obtained like this. The 10 is equal to 60 over 3 factorial. And the 60 was the number of arrangements of 5 objects, and that is 5 factorial over 5 minus 3. Five minus 3 is 2 factorial. So 5 factorial divided by 2 factorial is 5 times 4 times 3, right? That's what we had. So this part here is really 5 times 4 times 3. Okay, so the numbers in this formula are just 5 and 3. The total number of arrangements, so the total number of subsets of 3 elements, each having 3 elements taken from 5 elements, is this thing here where you got 5 factorial over 5 minus 3 factorial times 3 factorial. 5 is the total number of elements in the set, and 3 is the number of elements in the subset. So I can actually create this 10 by using only 5 and 3. I can create this 10 by using, if you calculate this, you'll get that, okay, as we saw. So that leads us to something which is quite revealing. It tells us where you can actually solve this problem in general. So in general, a set having n elements has this number of subsets in it. N factorial over n minus r factorial times r factorial. Now, I'll come back to this thing here just now. Okay, so this is the formula now. You see, I can have any number of elements in the subset. Maybe I can have 15 elements in the set, and I want to choose a 3-element subset. Then you put n equals 15 and r equals 3, and you can calculate this. Your calculator actually calculates this for you. I'll tell you a little later how that works, and then that will give you the number of subsets. So you've got a very nice formula to find the number of subsets if each subset has got r elements and the set itself has got n elements. Now this thing here is a much simpler way of writing it without the factorials. Now I want you to just note see, at the last talk, I just want you to notice this thing. So we say that the answer to our question, let's not write down the question all over again. The answer is, whatever the answer is, and you got r objects at a time, and the number of each of those selections can have r factorial arrangements, as we had 3 factorial. And when you multiply all these, you get this thing here, n factorial over n minus r factorial. But we saw that this is really, you got r terms here. You have to choose r from n. The first one can be chosen in n ways. The next one can be chosen n minus 1 ways, and so on. And you stop as soon as you have chosen your r objects. So this part here is really n times n minus 1 times n minus 2, all the way like that. I'll say to r factors. That's very much easier. We saw in the box notation, we just put down these numbers, multiply them out. We didn't use all this complicated formula. So this is a much neater way of writing this, but this has got a lot of advantages, that formulation. But in practice, we use this thing here, right, for that. And so your answer is multiplied by r factorial gives you that. So what you have here is you have to divide this thing here, n into n minus 1 times n minus 2, all the way. You go and stop at r factors. The moment you have r numbers there, you stop. And at the bottom, you've got r factorial. You're going to divide by r factorial. So at the bottom, you've got 1 times 2 times 3. Also, this has also got r terms in it. So this gives you a very nice way of handling this thing. You put R terms at the top, R terms at the bottom, but here you start from N and you come down until you come to R terms, and at the bottom you start from 1 and go up to R, and that number is equal to the number of subsets having R elements. See? So this is equal to the number of subsets. By answer, I mean this is equal to the number of subsets. To cut down language, we say number of R element subsets. So that gives you a very nice clean formula for this thing. Now this rather cumbersome thing can be written. I'm just going to go to that page because I've written the notes to this. Okay, so if I go down, what's going on here now? All right, so let's look at some examples here. A set has 10 elements. The number of subsets having 4 elements is, so there it is, starting from 10, you go down until you have 4 terms, so this is R, and at the bottom you get 1 times 2 times 3 times 4. Straight away you can calculate this, you can use a calculator, but I don't, where possible, I don't use calculators, as you would know by now. So what I would do is, I'll say 4 times 2 is 8, I cancel, and 3 goes into 9 3 times, so it's 10 times 3 times 7, 3 times 7 is 21, 21 times 10 is 210. See, so there's a very easy way of calculating this. Instead of multiplying all these numbers and dividing by this or using a calculator, if you use your just cancellation, it can be done. That doesn't happen all the time. Sometimes you have to use a calculator, in fact maybe most times, but if you can be done, you go ahead and do it like that. There's another one. If you got, this is an example, we have to use a calculator. A set has got 20 elements, right? How many subsets does it have having 5 elements? So I should have been a little clearer. It has, this thing has got so many, I'm going to call it 5 element subsets. Right. There's an error in the solution, in the statement, the way I'm saying it. So if you want to know how many 5 element subsets there are, then the way to do that is you start from 20 and you go 5 down, 9, 20, 19, 18, 17, stop here because you got 5, 1 times 2 times 3 times 4 times 5, and then if you use your calculator, you'll end up with 15,504. So that tells you how many subsets. If you've got 20 elements in it and you're choosing a subset having 5 elements, you've got a very large number of subsets, over 15,000 such subsets. So it is so these numbers can be quite large. Okay, so if you, at this stage, I just want to introduce a notation. This thing here, which we are calculating, right, which we saw is the same as n factorial over n minus r factorial times r factorial, right? It's written in a simple way, using this notation here. You put a round bracket and you put an N at the top and you put an R at the bottom, nothing in between, just no spaces, no lines, nothing. You just put two numbers. And this thing here, whenever you see this, you must remember it's equal to this. Or if you like, it's equal to, you multiply, start from N and you go up to R factors, and at the bottom you got 1 times 2 times R. This object here can be calculated using that formula or that formula. And there's another formula which is used, and it is this. Another notation with a C there and N, a small n at the top and a small r at the bottom. Right. Now the symbol C and the symbol P, we saw P earlier on when we did arrangements. I should say that the P in NPR equals, the word is permutation. I've introduced this word to you before. And the C in NCR equals combination. And they use the word combination. Yeah, I rarely use that word. I normally use selection. In how many ways can you select R objects from N objects, right? The word combination doesn't say too much. Okay, so for example, now we calculated this one here. If we had 5 objects and you're choosing a subset having three elements, then this thing here, the number of subsets, each having 3 elements from 5, we calculated to be 10. So this is the notation, 5, this. And sometimes we read this thing as 5 choose 3. That also is a nice way of saying it, because we are choosing 3 elements from 5 elements. So the C, sometimes people use that for choose rather than combination, which is a much more sensible thing to do. Okay, so likewise now, if we went on to if you choose another example, this we saw 10 choose 4 is 210. I'm reading this as 10 choose 4 now. Or we saw in the last example 20 choose 5 is 15,504. And if you use your calculator, you can actually verify this. There is a symbol on your calculator. If you look for the symbol, you'll see NCR, and check. Better change my color to the original. Use calculator. To verify. (20C5) equals 15,000. Okay, you can. I'm not going to do it, but you can use your calculator and look for NCR. That's what you have to look for, and then plug in the value for N, which is 20, and R equals 5, and you should come up with 15,504. Okay, so let's get on with this. So the next question is, okay, let's do an example, another example. A bead worker is threading beads onto a straight wire. He has 4 green beads and 2 red beads and will use them all. How many different arrangements can he make? Now this is a problem on arrangements. So it's a problem which belongs to the previous section, but this is perfectly in order. So what have we got here now? Let's just analyze this. He's threading beads onto a straight wire. So he has a straight wire. Let's kind of draw the wire here like this. And then we say that he's going to thread beads onto that. So let me use my nice colors here. And he's going to thread beads. But he's going to thread 4 green beads. So he's going to put, maybe I should choose something first. So you got 4 green beads. And he has to choose 2 red beads. So you can put those 2 red beads anywhere. Like that. And there it is. He's got a pattern. So the question is, how many patterns does he have? How many different arrangements are there? All right. Now this is very similar to what we had before. You can think about it, and I'm going to go straight into the solution. Let me just, maybe I should go further down so you don't see the solution. Suppose I go further down the page. Right. So what happens now is, if you think about this, really what we are doing is we want to put 2 red beads and 4 green beads. So let's just stick in the green. Let's do the green beads first. Green beads, not green beans. All right. So you got, if you put the green beads in here, so the problem is I can put the 2 red beads anyway, right? And I'll get an arrangement. You will always have 4 green beads. Suppose they are there already. So now the question is, I must now stick in the red beads. And how many ways can I do that? Now, if you think about that, you're going to stick in the red beads. You've got several choices. You can put the red beads in this, let's put a vertical line for that. So you can put a red bead in here or here, right? Or you can put so to actually put a red bead, essentially you have to find 2 spaces. You must fill 2 spaces, right? And with reds. And the question is, in how many ways can you actually fill the spaces? You can fill this part here. You're allowed to put it, because the red bead could be at the end. Or you can fill it in this space, or you can fill it in this space, or you can fill it in this space here, as we did. But you can also put the red bead at the end on this side and fill that space, because the red beads can be at either end. So in effect, you've got 5 spaces. Oh, actually, you could put 2 red beads on one side as well. I could have 2 here. I could have 2 here. So these 2 lines they don't have to be in two different places. You can put them together like this. See? So the question is, okay, sorry, I had to take a break there. We'll come back to where we stopped. So the actual problem here was, let me just get back to where we were. Yeah, so the actual problem is, now you've got 4 green beads and 2 red beads. So let me just start this thing all over again. What we need to do is to put 2 reds amongst the 4 greens. All right, and how do we do that? So we need to have 6 spaces, in other words. And so let me draw something which has got 6 spaces in it. So you could have you break it up into 6 blocks like this. Sorry, they don't look very nice. So instead of putting 4 greens, I'll just put the 2 reds. I'll choose 2 reds and put them in, right? Anyway, so what you're going to do is, which is just two reds randomly, anywhere here. Right? And the moment I choose my 2 reds, then the rest of it will be filled with greens. So you can put those 2 reds anywhere. They could be next to each other, or they could be here, or they could be there, or whatever it is. So the problem is to choose 2 red spaces from 6. That is really the problem, right? The problem is to choose 2 reds from 6. We need to fill 2 of the above boxes. With reds. The rest will be greens. Right. So therefore, the number of ways is simply 6 times 5. This is the old problem. How many ways can you choose 2 from 6? And that is 15. Or in our new method, or it'll be, you're going to choose 2, so it's 6 times 5, right? You're going to choose 2 only, at the bottom you put 1 times 2, and you'll see this is exactly the same thing. If you use this new method, you're going to land up with n into n minus 1 over 2, as you can see. So that's a special case. That's a special case of what we have just said. All right, so if you get on to the next problem now, you just example 4. A chess set has 32 pieces, 16 white and 16 black. The white pieces are, all right, now if you played chess, then you will know what the pieces are, but I'm going to explain to you what these what the chess pieces are. You've got let's just write this thing down. Okay, let's read the first question first. So you've got 16 white and 16 black pieces, and the white pieces, they explain it is going to be 1 king, 1 queen, 2 bishops, 2 knights, 2 rooks, and 8 pawns. And same similarly for the black pieces. Now Kenny chooses 2 of the 32 pieces from a chess set. How many different choices can he have? So he chooses 2 pieces at random, right? And how many different choices does he have? So now that here we have to think very carefully about this problem, because all right, so what have you got? Let's just see what we've got here. We've got 16 pieces. You've got pawns for a start. You've got pawns. You got black and white. You got 8 black and 8 white. And then you have, apart from the pawns, you've got, let's start with the king. You've got 1 king, black king, and 1 white king. And same with queens. You've got 1 queen there. And next one is a knight. We'll use N for knight, not K. The K we already got for king. So we put a knight, but we've got 2 knights now, see? Each side you've got 2 knights. And then the next one is a bishop. Actually, the bishop should come first if you're setting up a board. You've got 2 bishops, the same color. And then right at the end, you've got the rooks or the castles, and there are 2 of these. Okay. Now, you're going to choose 2 at random. So you have to be a little careful here, because you have to decide if they are different pieces. Suppose the 2 chosen are different. In other words, I can't choose 2 black pawns. They are the same. But I can choose 1 black pawn and 1 white pawn. Right? So, how many groupings have you got here? You've got, that is 1 grouping. All the black pawns put together. All the white pawns put together. The king is a grouping. The white king and the white queen. The black, the same, yeah. And you got, so each of these is what I call a grouping. And how many have you got? 3, 6, there are 12 groups. And from each group, you're going to choose 1, because you only want to choose 2 pieces. So you will choose 1 from each group, and they are different. So you choose 1 from each group. So the first one you can choose in 12 ways. First can be chosen in 12 ways. So suppose I choose the first one from here, knight, this one here. Then the second one, I can choose it from anywhere else, and it will be a different piece. And there are 11 of them. Right, but this is really choosing 2 from 12. So it's 12 times 11 over 2. I shouldn't say this. This is not what you're going to do. This is a choice. This is not a permutation. So you're going to choose 2 from 12, and the answer is 12 times 11 divided by 2. Now that is if the 2 chosen are different. But if they are the same, then you're going to have That means I could have chosen 2 black pawns. Right? So you could have had, let's put, we'll have a notation. We use small letters. For black and caps for white. Then what do we have? We have, they both are the same, right? So I'm going to go down. We had 66 there. I'm going to so you'll have 2 black pawns or 2 white pawns, right? Or you could have 2 black knights or 2 white knights, or 2 black bishops, 2 white bishops, or you could have had 2 rooks. So these are the only cases where they're the same, because there's only 1 king and there's only 1 queen. So you can't choose 2 kings of the same type. But you can choose 2 of anything. So these are also additional possibilities. Additional possibilities where you got 2 of them are the same. So there are 8 of them. 8 in number. So in addition to the 66 where you had all, the choice was different, and you add them where the choices are the same, you're going to have 74 possibilities. Okay, so that is the answer to that question. Okay. All right. So now the next one. Okay. Yeah, you got this problem here. The inhabitants of Lottoberg, a small town with a population of 9,500 people, were determined to win the national lottery. The organizers of the lottery randomly picked 6 different numbers ranging from 1 to 50. And anyone who guessed the numbers would win 1 million rands. So you have to guess which 6 did the organizers pick. Now, the people, the inhabitants, they had to make their selection on a ticket, each of which cost 1 rand. So they buy a ticket and they make a selection on that. They pay 1 rand for the ticket. Now each of the inhabitants, they were determined to win the lottery, you see. So they said, look, we're going to buy a lot of tickets, right? And we're quite prepared to invest a large sum because we want to be guaranteed of winning. Right? Somebody here in our town should win, right? So what they did was, each one bought 1,000 rands worth of tickets. So they had 1,000 different choices. And each of the 9,500 people did this. And no 2 tickets were the same, had the same selection of 6 numbers. So they organized in such a way that if any one person chose 1,000 numbers, he chose 1,000 different numbers, and every other person chose a new set of 1,000 numbers. So there were 9,500 sets of 1,000 numbers. There were lots and lots of tickets, also so many different choices. But the remarkable thing was, yet no one won. And the question is, explain why no one won. Okay, so this is a nice problem to show you the futility, right, of gambling. A lot of people, they go for these, the national lottery in this country, hoping to win. But you can see that even if you have 9,500 people, each one buys 1,000 tickets, it's still possible not to win. So I hope that tells you a big story, okay? So let's have a look at this. How to go around doing this thing. You understand the question, so I'm not going to show you the question again. We can just go on to the... All right. So what we are going to do now is analyze this thing. First, we want to find out how many possibilities are there. So we first need to find and this is the point, the number of possible selections altogether. Now remember, we need to choose 6 numbers from 50 numbers. So we need to know how many ways can this be done, and we have actually done this. The way to do this is to choose 6 from 50 numbers. So it's 50 times 49 times 48 times 47 times 46. That's 5 numbers. And then you got 45. And then at the bottom you got 1 times 2 times 3 times 4 times 5 times 6. So that's the number of ways in which you can choose 6 numbers from 50. Now I calculated this, and I used a calculator, and I have the answer 954. I'm sorry, 95. 95344 2 0. See? So this is actually, maybe I should write this nicely. This is 9534420. So this is 9,534,420. Right. So that's the total number of possibilities. And these lotto burgers, I think they were called lotto. So those people who live in Lottoburg are called lotto burgers. Sounds like a large hamburger, cheeseburger, lotto burgers. All right, so lotto burgers selected, chose 9,500 times 1,000. Maybe I got too many zeros here. This is 9,500,000. Okay, no, that's fine. So that makes 9,000. Now you can see where we are getting to. They, with all their manipulations, they were only able to buy 9.5 million tickets. Okay, so Sorry, I'm just getting a little bit mixed up here. Okay, only that. So therefore, the winning ticket happened to be in the remaining ones because the other one had. So their luck was completely out because, as luck goes with gamblers, the winning ticket must have been, writing is very bad, sorry, must have been amongst the remaining tickets. So no one won. So that's the explanation, right? Because you had more possibilities than the number of tickets. But mind you, if there were 9,600 people, somebody would have won, because that would have exceeded that number. Then you would have had 9.6 million, which is greater than the number that we had. So this town was unfortunate that it had just too few people, slightly more or less. Okay, so that takes care of that, and I think we're going to stop there. This has been a very long lesson. I didn't stop after 1 hour as I normally do because I wanted to finish this thing off. So I thank you very much for having the patience to listen to this entire lecture, and I trust that you have a proper understanding of how to count, because there are different ways of counting. So just to sum up, we had the first counting principle, the first counting principle. I'm going to go through this thing very quickly. Then we had the second counting principle, and then we spoke about number of arrangements, n factorial arrangements of n objects. And then if you want to take r objects at a time, we saw that you're going to have this, which is a fancy way of writing n times n minus 1 all the way to r factors. Okay, so these were the first few things that we did, and then thereafter we continued with, we said we looked at the number of R element subsets. If you have a set having n elements, and that is n factorial over n minus r factorial times r factorial, and that is another way of writing this thing. It's a much better way of doing this. You have r factors at the top, and then at the bottom it's 1 times 2 times 3. You have r factors at the bottom, but that's r factorial. Okay, and this is the theory in all this, and then we found that this is total. Okay, I think there is still another, if I'm not mistaken, there's just still one other problem left here. Let me just check it out. Are there any more here? Hey, in fact, there's more, man. My goodness. Okay, you got this problem here, and sorry, I thought I'd finished. So how many numbers between 100 and 999 have the digits in strictly increasing order, right? So in other words, like 459 is such a number, but this one is not strictly increasing. 455. So how many such numbers are there? Well, if you think about this, you got a 3-digit number. So the number could start with 1. Let's suppose it starts with 1. Or it could start with 2, or 3, or 4, or 5, or 6, or 7. Right? Well, it can't start with anything bigger than 7, because it's a 3-digit number and they're in increasing order. Right? So in this last one, there's only one number which will fit this bill here, namely 789. But what about these now? How many of these numbers start with 1? Well, you've got 8 numbers to choose from. 2, 3, 4, 5, 6, 7, 8, 9. Right, 1 is missing. So, oh, I'm counting 7 twice. Okay. So 5, 6, 7, 8, 9. So the 8 numbers here. Now, if you choose any 2 of these numbers, you can get a strictly digit numbers. For instance, if I choose 76, 7 and 6, then I can write 167, but not 176 will be out. So if I choose any 2 of these, I get exactly one number, which will be an increasing number. So I have to choose 2 numbers from 8 numbers. And the number of ways you can do that is 8 times 7 over 2. This is the same problem. The number of ways of choosing 2 digits, 2 digits from, 2 numbers from, in fact they are digits from 8, and that gives you 28. See? Now if you start with 2 now, right, you want to strictly increasing, you got a smaller set, 3, 4, 5, 6, 7, 8, 9. There's 7 of them. So here it's 7 times 6 divided by 2. That gives you 21. And likewise, it's 6 times 5 divided by 2. That gives you 15. Or you get 5 times 4 divided by 2. That gives you 10. And you have 4 times 3 divided by 2. That gives you 6. Or you have 3 times 2 divided by 2. That gives you 3. And then 1. So if you want to know how many there are, you have to add up all these, and that will give you the total number of such numbers. We've taken care of every one of them. So the trick was to get the starting point, fix the starting point. How many in the 200s, how many in the 300s, and so on, and then add up everything. And if you work out all this, you get 49, 64, 74, 80. You get 84. So there are 84 such numbers. All right. I think by now you should be getting the picture. And the last one, I think, a set has got 7 elements. How many subsets does a set have? Okay, so it's got 7 elements, and you want to know how many subsets it's got. And so you can say, well, include the unique empty set. So what we do is the number of elements in the subset. So you have to count it in each case, number of elements in the subset. Suppose it's 0. So there you have only one empty subset. If the number of elements in the subset is 1, right? You got a set which has got 7 elements: A, B, C, D, E, F, G. So the one element subset will be A by itself, B by itself, and C by itself, and so on. And you can see that there's going to be 7 of them. Right. But now, if you've got 2 element subsets, now it becomes, the first thing that we did was 7 times 6 divided by 2, and that gives you 21. And if you take the number of 3 element subsets, that is 7 times 6 times 5, over 1 times 2 times 3. If you work that out, you get 35. Right. Now, I said earlier on, the number of 3-element subsets will be the same as the number of 4-element subsets. I don't know whether you remember that. Because 3 plus 4 is 7. And we are looking at, for instance, there we had a set ABC, and we said you leave out DE. So it's the number of 3-element subsets is the same as the number of 2-element subsets, because there were 5 elements, 5 sets, 5 elements in the set altogether. So here, the number of 4-element subsets, we are working with 7, will be the same as 35. If you calculate it, you'll see it's like that. And the number of 5-element subsets, if you calculate it, you'll see it's 21. 6-element subsets is that, and the number of 7-element subsets, we're taking the whole lot, is clearly 1. And when you add up all these things, you're going to get 128. Now notice, that's the answer. See? Now 128 is a kind of a familiar number. Is this a coincidence? This is also 2 to the power of 7. I'm not putting it next to that, otherwise it will be a factorial. So it's 2 to the power of 7. So the number of subsets that a set having 7 elements is 2 to the power of 7. Is that a coincidence? The answer, it is not. If you try it with 6, you will see you get 64. Right? So it's interesting. If you try it with 5, you'll see the same kind of a thing. If you had with 5, you have 32. And so on. What I mean is, number of, if you said a set has 5 elements, right? How many subsets does it have? The answer is 2 to the power of 5. See? So in general, a set having n elements has 2 to the power of n subsets. There is a fancy way of proving this thing, but we can try it out with n small enough, and you see there is a pattern, and it works. It works for no matter what n is. Even if you've got 1,000 elements, it's got 2 to the power of 1,000 subsets. Okay, and I'm sure that this is the last question. So I thank you very much for listening, and it was a long haul, and I trust that you will have an enjoyable day from this point onwards. Thank you for listening.